Welcome to the third lecture of the module on astrophysics of neutron stars. In this one, we will talk about some more radio pulsar phenomenology. Now, let us go back to the structure of the neutron stars for a little. The stellar structure of an active star is given by these 5 equations, as you know: the hydrostatic pressure balance equation, the equation for energy generation, the equation for energy transport, the equation of state, and finally, the mass radius relation. Now, for the compact objects, the compact stars to be specific, the equations governing these compact stellar objects are only 3, because there is no energy generation and therefore, no energy transport. So, all we have are hydrostatic pressure balance equation, the equation of state, and the mass radius relation. And we also must remember that there is no temperature in the system. That does not mean that the system, the compact star, is actually at 0 temperature, but as we have seen in a previous module, the temperature of a neutron star, the real physical temperature of a neutron star, is much smaller than the Fermi temperature of all the relevant particles there. Therefore, the physics of the equation of state does not depend on the temperature. Now, various other physics, very importantly transport properties on which magnetic field evolution is dependent, would definitely depend on temperature, as we will see later, but for the equation of state there is no temperature. So, for active stars, nuclear fusion is going on and the pressure of gravity is supported by the gas pressure, which is dependent on temperature, plus the radiation pressure. For dead stars or the compact stars, there is no energy generation. So, the pressure is the pressure of Fermi degeneracy plus other kind of pressure. Now, for white dwarfs, as you already know, the pressure is given by degenerate electrons plus a small fraction comes from the underlying ionic crystal. The densities range from 10 to the power 6 to 10 to the power 9 grams per cc. By density here I mean the central density, and the pressure is given by the relativistic electrons and it scales as rho to the power 4/3. Now, for neutron stars, it is basically the degenerate neutrons which govern the equation of state and whole lot of other physics of neutron stars, plus there is degenerate protons and electrons. They have their roles in controlling some of the physics also, as we will see later. At the high density, the average density, you must remember, is order of the nuclear density. Such high densities, the nuclei dissolves and there is preferential beta capture. The protons combine with electrons to generate neutrons and energy goes away in the form of neutrinos, antineutrinos in this case. The pressure at these densities are basically provided by non-relativistic neutrons, non-relativistic in contrast to the relativistic electrons. In neutron stars there are relativistic electrons also, but the pressure component is negligible. The pressure that is coming from such relativistic electrons is negligible. The pressure is coming from the degenerate neutron gas, but there is also a significant amount of pressure that is coming from the nuclear interaction of neutrons and a small amount of protons. The state of the matter is like this. The crust is metallic in nature, it behaves like a metal. The outer crust, where the density is less than rho drip, we already know at this density free neutrons drip out of nucleons, because the nucleons become so neutron rich that the neutron energy levels hit continuum. That is, there are neutrons, if they have to be accommodated in a nucleus, their energy levels become so high that they can become free of the binding of the nucleus. So, before that density, that is the drip density, is reached, we have degenerate electrons and neutron rich nuclei. Before the drip density is reached, neutron rich nuclei in the lattice spaces in the outer crust. In the inner crust, where the density is larger than drip density and smaller than the nuclear density, we have degenerate electrons plus neutrons, these free neutrons which become superfluid there, and also neutron rich nuclei. A word about the drip density. Traditionally, the drip density is estimated to be about 4 into 10 to the power 11 grams per cc. Now, this is calculated for cold beta stable material, but a neutron star may not always be very cold beta stable. In particular, for accreting systems, the temperature of the crust goes quite high and also the composition changes there. The material is no longer beta equilibrated, and in such systems recent work has shown, in particular work by Chamel et al., that the drip density could become much higher. Nevertheless, it is of the same order of magnitude and we would not discuss much about that here. And the core is expected to be superfluid. It has relativistic degenerate electrons, superfluid neutrons and superconducting protons. Deep inside the core, one is not really certain what kind of material is there. There could be exotic phases, kaon condensates, hyperons, quark matter. That part has not been understood with any certainty yet. Now, because the neutron star is mainly superfluid, the neutron component both in the crust and in the core is superfluid. The rotation is supported by creating vortices in the neutron superfluid. We will talk about this a little more in the next lecture. And the magnetic field is probably supported by superconducting fluxoids and or crustal currents. Now, here is a mandatory pi diagram, a slice through the neutron star. Now, outside there is a very thin layer of envelope in the gaseous or in the liquid form. only a few centimeters. The outer crust, the solid crust, starts from about 10 to the power 8 to 10 to the power 10 grams per cc. It is a solid lattice, as I have mentioned. Then at the boundary of the outer crust and the inner crust is at the drip density 4 into 10 to the power 11 grams per cc. In the inner crust we have superfluid, which is a singlet state of the neutrons, spin 1. In the core region, which is something like order of the nuclear density, we have uniform matter in the sense that the material is not in the form of nucleus and electrons, but all the nuclei have dissolved now. We have a proton superconductor, which is again in a 1s0 configuration, that is a singlet state, whereas the neutrons are now in a triplet state, in a 3p2 configuration. And as I have said, we really do not know what is happening in the inner core. Now, one word of caution, not to take the dimensions shown in such a picture very seriously, whereas the order of magnitude of all the numbers are correct, the precise numbers of the radius at which various phenomenon is happening would vary from equation of state to equation of state, and so would the total radius of a neutron star. Now, there is a very interesting phase of matter in the core crust boundary. Now, this is a slice through the densities shown in a different way. So, here we have the envelope, the very thin envelope, the length scales are arbitrary in this picture. So, in the thin envelope the material is normal. In the outer crust the particles are coming very close. This is where we have the neutron drip. So, here we have free neutrons as well as the electron gas in the interstitial spaces of the lattice, and at a much higher density when we are approaching the core crust boundary, that is where the nuclei now no longer retain their spherical shape. So far they were all sort of spherical, which is a normal spherical shape we see in terrestrial conditions. So, in such high densities, we are close to the nuclear densities, the nuclei become flattened, they become like plates or like spaghetti, and the structure of the matter changes considerably. This phase is known as the pasta phase, and recent research is investigating these phases, and there is some indication that this phase, even though the total amount of material in this phase is small and it spans only a small region of the neutron star, they may have very important role to play in the overall evolution of the neutron star magnetic field. This is a plot which you may have seen earlier, shows different kinds of equations of state in a mass radius plane, and these horizontal bands give us the measured masses with uncertainties of observed neutron stars. So, here are these observations. Now, this plot comes from a paper which is almost a decade old now. The recent mass measurement which has been available only a few months ago pushes this bar a little higher. So, now we have a confirmed mass measurement of 2.14 solar mass. So, somewhat here, and that gives us a constraint on the equations of state. There is also another way to constrain the equations of state. A constraint on the equation of state basically tells you what kind of material is there inside a neutron star, and as a consequence what is the way such material behave. Because one has to remember that such high material at effective 0 temperature cannot be probed under any terrestrial laboratory conditions. So, neutron stars basically behave like huge physics laboratories in the sky. So, the other way one can have an handle on the equation of state are from the cooling curves, the cooling behavior of neutron stars. Here are some theoretical cooling curves. So, for example, this n, the curve marked by n, this is for pure nucleonic matter, that is neutron, proton and nothing else inside a neutron star. On the other hand, here is a curve which corresponds to normal neutrons and superfluid protons, and this curve corresponds to superfluid neutrons as well as superfluid protons. Of course, because protons have charge, they are superconducting. So, both the components inside the core are superfluid, that gives this kind of a cooling curve. The interesting part to note here is this bit which has been zoomed here, and these red points are observational points, and we can see that these points are following the curve which has both neutrons and protons as superfluid very closely. So, perhaps that is the true state of matters inside a neutron star. Now, as we have said, there are two different kind of superfluids inside a neutron star. Here is a figure showing pairing energies of protons and neutrons inside the neutron star as a function of the Fermi wave number or Fermi momentum, if you wish. Now, one has to remember that even though protons and neutrons are two states of the isospin, so to speak, they cannot form pairs, they cannot form effective Cooper pairs to form a single superfluid inside a neutron star, because the densities of the protons and the neutrons are different. neutrons comprise 90% of a neutron star by mass and protons comprise of only 10%. So, therefore, the Fermi energies of protons and neutrons, even though both the components are degenerate, are different. So, the energies at the Fermi surface of these two particle species are different, and therefore, the pairing cannot happen between a neutron and a proton. So, protons and the neutrons form superfluids separately. So, here is pairing energy curve for a neutron singlet. This is for protons. Protons form singlet state superfluid inside the core. Neutrons form singlet state superfluid in the crust, and here is it for the neutron triplet pairing which happens inside the core. Now, here is another way of seeing the same physics by looking at the critical temperature for superfluid transition inside the neutron star. It goes in increasing density in this direction. So, this is the inner crust. In the outer crust there is no superfluid, of course. In the inner crust neutrons are superfluid and the transition temperature goes like this, whereas for the core the transition temperature for the neutrons is like this and for protons are like this. So, we see that there are two different superfluids having different transition temperatures, actually 3 different superfluids, because the neutron superfluid in the inner crust is different from the neutron superfluid in the core. So, there are 3 different superfluids with different characteristics inside a neutron star. Now, when you consider neutron superfluid inside a neutron star, we have to remember that a superfluid can only rotate by creating rotational vortices, which are nothing but a quantum of circulation inside the superfluid. A superfluid cannot rotate like any other macroscopic fluid, because it does not have any viscosity, and therefore, 0 viscosity liquids cannot rotate, cannot take the angular momentum from the container, so to speak, and therefore, the only rotation a superfluid can sustain is by creation of vortices. Now, these quantum of circulation has an unit of angular momentum associated with them, which is given by this quantity. Because we are dealing with a neutron superfluid, the mass of the particle would of course have to be the mass of the neutron, and therefore, inside a neutron star the quantum of circulation that a neutron superfluid would create has this kind of angular momentum. And now, to support the rotation of a neutron star, which has a mass of maybe 1 to 3 solar mass, somewhere in within that range, we need a huge number of such quantum. So, if we consider a typical neutron star of, let us say, radius of 10 kilometer and rotating with a spin period of 1 second, we would need something like 10 to the power 16 such rotational vortices inside the neutron star to support its rotation. Now, let us consider the proton superfluid, which is a superconductor, because protons are charged particles. Now, there can be 2 kinds of superconductors we know from our terrestrial laboratory physics. These are called type 1 and type 2. The type 1 superfluid superconductor would have a critical field called Hc. So, if the external field is less than this critical field Hc, then the material would be in superconducting state and no magnetic flux would penetrate that material. So, that is a type 1 superconductor. There is another kind of superconductor called type 2, and it has not one, but two critical fields Hc1 and Hc2. Now, what happens is that there is no flux penetration beneath the value of Hc1. So, if the external field is less than Hc1, there is no flux penetration, but if the external field is greater than Hc1, but less than another critical field Hc2, there would be flux penetration inside the material, but would still be in a superconducting phase. The superconductivity gets destroyed only when the external magnetic field is larger than this second or the upper critical field Hc2. And we believe that the proton superconductors inside a neutron star are of this second type. On the other hand, if it is in a superconducting phase of type 1, there would be no flux penetration inside a neutron star, the core of a neutron star. Now, the magnetic fields that are seen in magnetars, they are rather large. If the core is a type 1 superconductor, then there will be no flux penetration and magnetar kind of field would be difficult to support in the thin crust that a neutron star has. So, quite likely the neutron star is a type 2 superconductor and the flux penetration has happened at the time of the creation of the neutron star. Because what we are saying at this point is that if it is a type 2 superconductor, then the flux is between the first critical field and the second critical field, and it got frozen in when the neutron star was born. So, here is the transition temperatures, the density dependence of the transition temperatures of the proton superconductor has been shown. This cyan colored curve shows the transition temperature in units of 10 to the power 9 Kelvin. The critical fields Hc1 and Hc2 are shown by these two dash dotted curves in units of 10 to the power 16 Gauss. Now, just like neutron superfluids must create rotational vortices in order to support rotation, a superconductor must also create fluxoids in order to support a magnetic field, and the quantum of flux that such a superconductor creates is of this magnitude 2 into 10 to the power minus 7 Gauss centimeter square. So, now once again we see that the number of flux quanta that which are again nothing but rotational vortices, but of charged protons, the number of such flux quanta that we require for a neutron star which has, let us say, a magnetic field of 10 to the power 12 Gauss would be 10 to the power 31. So, we need as many rotational vortices. So, therefore, a neutron star to support a moderate rotation, moderate in the sense the kind of spin period that we observe in neutron stars of 1 second or so, a moderate magnetic field of 10 to the power 12 Gauss, it would have to be threaded by 10 to the power 16 rotational vortices and about 10 to the power 31 magnetic fluxoids. And if the magnetic field is larger, like if it has magnetar fields, then the number of flux quanta would go on by 2 or 3 orders of magnitude. We also must remember there is another critical aspect of superfluidity in the case of the neutron stars. The neutron superfluid and the proton superconductor both are nucleonic superfluids. So, neutrons and protons would interact with each other via nuclear force. So, therefore, these two superfluids and consequently the two sets of rotational vortices would be interconnected. They would be, so to speak, they would be interpinned superfluids. So, therefore, the movement of any kind of rotational vortices which would be required, we would see in certain situations, would be complicated by their interaction with the other set of rotational vortices. Now, we talk about another important aspect of radio pulsar behavior. This is a picture of Vela pulsar, one of the very well known radio pulsars. In October 1968, astronomers from the Sydney University discovered a pulsar with a period of 89 millisecond in the Vela constellation. The Crab pulsar was found the next month by astronomers from the Green Bank Observatory. Now, both of these pulsars are very important in the phenomenology that we are going to discuss now, that is the phenomenon of glitch. The first glitches between February 24 and March 3, 1969, immediately after it was discovered just about a year ago, Vela was found to pulse more rapidly than before. So, its spin period has become shorter. The rotational frequency had increased by a factor of 2 into 10 to the power minus 6. The increase in the spin down rate, that is delta omega dot by omega dot, is about 7 into 10 to the power minus 3. A smaller glitch, not of this large magnitude, was also observed in the Crab pulsar in September 1969. Since then, both Vela and Crab have been showing this kind of period glitches every now and then. They are repeating this behavior over all these years that they have been observed. While Vela mostly have large glitches, Crab mostly has smaller glitches. the glitch phenomenon a little more closely, what we see is this is the spin frequency axis, which is becoming smaller with time, which is the steady stellar spin down due to electromagnetic radiation and perhaps also partially due to gravitational radiation or whatever. This experiences a sudden increase in the spin frequency. So, it goes up and then it comes down and resumes its original slow down path after a while. Now, one has to remember that this resumption of the original slope does not happen for every glitching pulsar, but this is one of the characteristic features of the phenomenon of glitch. So, if we see it in terms of the period, the spin period is increasing, it is slowing down. So, it is the spin period is increasing, suddenly there is a jump in the spin period, it goes down and then goes up again. So, this sudden decrease in P, which is characterized by a change in the frequency. Now, the range of the fractional change of frequency is from 10 to the power minus 12 to as large as 10 to the power minus 4. Remember, the first glitch of Villa was 10 to the power minus 6, which was considered to be very large, but now we have seen larger glitches in many pulsars, as well as have seen extremely small glitches of the magnitude of 10 to the power minus 12 in millisecond pulsars. This is followed by a relaxation towards unperturbed P, which I have already said may or may not happen in every instance of glitch. This is one of the interesting aspects of glitch that has come about in recent years, because now we have accumulated a large number of glitch observation. So, in the last count, if I remember correctly, there is more than 500 glitches which have been seen in something like 200 radio pulsars, and therefore, now we can look at the nature of these glitches from a statistical point. And this is a very simple histogram of the magnitude of the glitches, and what is being clearly seen here that it is a bimodal distribution. This has been investigated by a number of people and certain conjectures have been made from this bimodality, and this appears to be related to the reason why we see glitches in radio pulsars. Now, there have been theoretical conjectures trying to explain these glitches. One is related to the superfluid dynamics, and actually this is the most accepted theory regarding the glitches. So, it is related to the spin down of the superfluid. As we have said, a superfluid rotates by creating a number of rotational vortices. Therefore, if it has to slow down, the only way it can slow down is by reducing the number of rotational vortices. Now, the neutron superfluid rotational vortices are pinned to the material in the inner crust, and this pinning has a particular energy associated with it. So, as long as the tension in the rotational vortices is less than the pinning energy, the vortices remain pinned to the pinning sides. Now, why are we talking about the tension? Because the neutron star is slowing down and the superfluid wants to slow down, and it is trying to expel these vortices from the superfluid, but they are tied to the pinning sides. So, therefore, a tension is created. When the tension is such that the pinning energy is exceeded, then there is mass unpinning of the rotational vortices from the pinning sides, and these vortices are then deposited to the solid crust. And remember, each rotational vortex is associated with a quantum of angular momentum. So, when these rotational vortices are deposited on the solid crust, the crust acquires an extra angular momentum, and then it starts rotating faster, and that is what is observed as a glitch by an external observer. So, we believe that such an unpinning happens when the frequency of rotation of the superfluid has a huge difference from the frequency of the rotation of the neutron star as a whole, that is the solid crust that we are seeing outside. So, when the difference between rotation frequency of the solid crust and the superfluid component exceeds a certain value, there is unpinning and there is glitch. Now, the problem with this understanding is, so far there has not been any predictability that has worked for these glitches. In other words, if the theory works, then we should be able to predict the next glitch of a repeated glitches like Vela or Crab pulsar. Now, that has not so far succeeded, a prediction of the next glitch. So, there are issues with the theory which still requires people to work on this. The other theory which has been offered, actually the first theory which has been offered to explain glitch is that of crust quake. It is very simple. The neutron star is solid outside and it is spinning down. Therefore, there is a centrifugal force associated with the spin, and the neutron star has in its past at certain point of time have acquired an ellipticity which is characteristic of the spin of that time, but as the spin changes, the ellipticity cannot continuously change because it is a solid, and therefore, mechanical stresses are developed in the crust and the crust cracks at a point when such stresses become very large, and this brings about a change in the moment of inertia of the neutron star crust, and that induces a change in the spin frequency. Now, it has been conjectured that whatever may be the underlying dynamics of the glitch, crustal energy may not be sufficient to explain the very large glitches that have been observed in recent times. So, perhaps the core has to be involved with the dynamics of the glitch. In summary, the glitch is likely induced by a catastrophic unpinning of rotational vortices because of some thermal pulse generated due to star quake, perhaps by crust cracking, by magnetic stresses near the core crust boundary, and the post glitch relaxation that is seen in many pulsars is caused through slow outward creep of these rotational vortices. There are some issues related to the phenomenology of glitch. The relation between glitch and flux expulsion, the dynamics of which needs to be worked out in more detail. The quantitative nature of expelled flux, whether glitch can induce field enhancement for radio pulsar to magnetar transition. This is a recent suggestion by certain observations which seem to indicate that there is an increase in the magnetic field in repeated glitches. Whether that is associated with appropriate correct time scales of radio pulsar to magnetar transition, these are all open questions for glitch phenomenology. Also the crustal microphysics in terms of its transport properties, the understanding of impurity concentration in the crust, etc., also need to be folded into the glitch phenomenology. In summary, there are likely two different origins for glitches, because we have seen two different origins have been proposed, and now when the number of glitches observed are large, a statistical interpretation also tending to hint at two different kinds of glitches, probably coming from two different physical origins. Seems to be some indication for glitch induced flux expulsion and increase in observable field. Perhaps multiple glitches can change an ordinary pulsar to magnetar, but these are really in the stage of conjectures. So, let us not take these issues very seriously at the moment. With more and more observations of glitch that are coming up, hopefully some of these questions would be answered.